Hello, everyone. Today we're going to be covering pulleys. This is part of AP Physics 1 physics, and yeah, let's begin. So, what is a pulley? Well, the basic key concept is that a pulley involves uh, two objects, right? And they're both connected. Well, it can be two or more objects connected by a string, or rope. All right. So an example could be, hmm, oh, a good example is the grandfather clock. That one's really good. Because technically, it's robust. The design is just a string and a ball, but it's very similar because they recreate the same motions. And so the tension in the string. So this is another key concept: is that the tension in the string and the acceleration of the object are the same because they're part of the same system, right? Well, they're not like, I wouldn't say the same, but they are connected, right? I think that's a better way to see it. So, um, another key concept. This one is more of a tip, really. Well, kind of like when you're starting off as a student or person doing these pulleys, is that we're going to be considering these pulleys to be massless. So massless pulleys are ideal because the tension is uniform all around, and we can ignore any type of other forces or rotations. That's in the future. I'm sure you'll love rotation. Is uniform. So massless pulleys are ideal because the tension is uniform. So that means there's a string here and a string there. These two will have the same tension, not affected by the actual involvement of the mass of the pulley. Because if the pulley, this you'll learn this later on, has a distribution of mass, you'll have to find the equation using calculus. You won't though. Um, that's for calculus-based AP Physics C, which is the same as AP Physics 1, but with calculus. And people who think they're cool and better for taking it are just a bunch of Asian. I can't say. Uh, silly me. Are just a bunch of tryhards. That's what I meant to say. Yeah, man. Anyways, so tips with pulleys. Uh, Use free body diagrams or FBDs for each jaw object. Okay. So just like inclines and many other problems, when you have a system connected by various other types of sorts and mechanics, um, you'll have trouble like isolating each one mathematically with only equations. So that's why we use free body diagrams or diagrams in general to be able to isolate these masses or these objects, and we can separate them. So separately. Okay. Number two tip. Um, Well, this one is kind of an assumption, but just assume this string is massless. And this is an important one. It's inextensible. Now, that does not mean it cannot stretch. It can definitely stretch, and that has to do with springs force, but it's kind of a different assumption. It's just it cannot be further stretched than its current max stretch, which in real life, obviously, you can do, but no. And then this one is obvious, and most of AP Physics one is that ignore friction or ignoring friction. This is in the pulley, so in the pulley. This is called internal friction, and it's something that has to do with just rotating mechanisms and also other forces. So you only need to consider the tension. So this would be the force of tension, Ft. Then you would have to do gravity, which is quite easy, just Fg or mg, mass times the acceleration, gravity, and then the normal force. And this is called Fn, aka Fn. An Fn. Oh, an Fn is bothering me. Yeah, the normal force. If it's touching a surface. If it's floating, no surface. So a common problem would be this: you have a cliff, you have a box here connected by pulley right here, then the string connected to another box. This one has no normal force, it has gravity, as tension, tension, normal force. But in this scenario, it just cancels out the normal force because it's not moving upwards or downwards. But there is normal force, you have to stay there. If you don't, guess what? They're gonna think you didn't know about it, even though you definitely knew about it. It's so obvious that you forgot to state it, and now you have minus marks because you didn't state it. And so you lose. And then you have friction right here. So that's just a common problem. I'll keep that up for now. And then remember F equals ma. You can always do that. Newton's second law. Newton's second law. You can always apply that very easy. Okay. So let's just come up with an example of what exactly pulleys are, what they look like, how to do them. Alright. So this is going to be a more accurate depiction of what I just did a few seconds ago. More detailed though. So let's say we have a cube with mass, and then we have a pulley, massless, and then we have it connected to a box with also mass. And now we have to draw the forces. Alright, so let's connect the forces. Well, first let's start with the floating cube. We have the force of gravity pulling it downwards, Fg, and then we have tension upwards. So, I think I should explain this, but if you're a bit confused about how tension works, it's just basically the force within the string that's holding it upwards or downwards or just in any like direction. So, let's say it kind of like it's a bit similar to friction, but it really isn't. But in case you're confused why the tension force is not going like downwards or something, that should be because let's say we put this cube on the natural state, right? It's just gonna fall. But because of the string, it's floating. That means this string is preventing the gravitational force. And therefore, that string force, the tension force, must be opposing its motion, right? So that's why we put it in the opposite direction. It's also because it's connected to this cube right here, and so the tension from this one is equal to this one, right? So ft1, so this is cube number 1, this is cube number 2. And see, this is where it can be confusing, because now you have a lot of forces going on with the same name and number. But it's okay, because in reality, you're not going to be using numbers, you're going to be using letters. Yes. This makes it a lot more simpler and less much confusing if you have dyslexia, right? Kidding, but it's you're gonna be wanting to use letters instead of numbers, because with numbers you get confused because you're starting to deal with other numbers. But if you use letters, it's so much simpler with numbers or with only variables. Like let's say you're doing a number problem with number things at the bottom, it gets confusing. You do it with letters, kind of simpler. And if you're doing variables only, which you will do in AP Physics, with numbers, it just gets really weird because you're not supposed to really have numbers in there, and you might confuse and putting a number in there by accident. And so, yeah. So FTA will be equal to FTB. So we can make a statement right there, equals to FTB. And so these two cancel out each other. And you can notice that they're kind of in opposing motions if you were to think about it in real life. And there we go. And then we also have the friction force. And we can call this mass A, and then we have mass B. And that's basically it. Now, key thing here is that it's attached by a string. So these, no, actually, let me write it here. These masses are attached by a string. Therefore, same acceleration. In this case, the acceleration would be due to gravity. And this is reflected in FT. Okay. And so let's break down the forces and do some net equations. Okay. And I'll walk through each one. Right, sorry about that. So let's actually do a statement for each mass. Okay. So let's say we wanted to, like I mentioned before, we want to isolate each mass or each object. And so I'm not sure where I made that statement, but I said that. I know I said that. And so let's just do it right here. This is an easy way to do it. So F net A, this would be looking at the mass A. We do have normal force and gravitational force, but they cancel out each other, so it's not necessary to stay here. It would only be necessary as to if, well, it's always good to do it, but not necessary. There you go. But you have FCA minus the force of friction. Okay. Then we break it down even more. We have the mass of A times acceleration. Remember, when you break down these forces with MA, you have to make sure you're using the correct mass, because if you just put M, it could be another mass within the actual problem slash equation. And so yeah, that can become a problem. So FTA minus mu Fn. So in case you need to find friction, you can do that. But we know that the friction and the thing are the same, so you can do MAG because the normal force is equal to the gravitational force in math A. Therefore, you can rewrite that normal force as mu MAG. And guess what? Now we can cancel the MAs. Yep. Guess what? You can't do that actually. Wait, no, you could. You could, but you don't have to though. But you can preferably not always cancel out the masses. But I was gonna say not because I saw the minus mark, but I forgot multiplying itself here. So, but yeah, just don't worry about it. And now for B. Oh, what is B dealing with? It's only dealing with vertical forces. So we have F naught. It's not moving sideways. So we have Fg minus Ftb. And as you can see, the Ft here is negative and the Ft here is positive. So then you would do Fta minus Ftb. And then this would equal to 0 because they're equal. So that's just another thing. So then we would do MBA equals to MBG minus FTB. Alright. So nothing too like crazy. And then this is what we call a system equation. So this is what you're going to be doing most of the time when this is called a set of equations. It's something similar to what you would do in math class. But basically, by finding these two equations, you can combine them or use them separately to find another variable. And so, if we took all the forces in the system combined of A and B, what would it be? Well, we take the positives first, so it would be Fg, then preferably you do the positives combined, but you can also do the actual like parts separately, like this. So you could do Fg minus Ftb plus Fta minus friction force. So you could do that, but you can also combine them, like as in the positives go together and then the negatives. Any of those are okay. Okay. Oof, sorry, my computer is getting quite hot. Right, so that's the system equation. Now we can just simplify it a lot more. In this case, now we can do MA, and then we can just define M as equal to MA plus MB. You kind of have to do these statements, or else it would make sense. So then you have MBG, and then these two cancel out, right? Remember, minus mu A. I forgot what it was. G, right? Yeah, because yeah, normal force. And then you can just simplify this a bit more if you want. It's not necessary, but you could also do MA and B times A equals G minus mu MAG. So that's a fully simplified one. This, all you're doing is just stating this into this. So yeah, that's just how you do a system equation. Let's say you have this one, yeah. So obviously, whenever you are dealing with these, isolate each object, each mass, try to identify the net equation and the forces. And when you're doing the free body diagram, what helps the most, in my opinion, is to draw the diagram out and put the actual FBD within the object in the diagram. And so you can kind of see right here in this example is how useful and how clear it becomes. especially when you start thinking about it in real life. I feel like maybe physics one specifically, you get to really like imagine these things going on in real life and how they occur, how they work, and that kind of helps a lot to situate what you're doing and whether it's right or wrong. Obviously, sometimes you'll encounter some problems that you know the AP department has come up with somehow. Those things are very close, and I'm telling you, they're nothing like real life. So just most of the basic stuff, you should stick to that. But yeah. Be confident though, it's fine. So let's do some practice problems now. So number one, here we go. So let's say oops, two blocks are connected by a string on a hmm, actually no, over a frictionless pulley. And that's kind of important to state that the pulley is frictionless. I don't have to state that it's massless because that is kind of implied. Yeah. So let's say that M1 equals to M1 can be 3 kilograms, and then M2 can be 5 kilograms. Right. So what's the question here? Well, find the acceleration of the system, right? Keyword system there. So that means the MA of the system and the tension of the rope, right? So even though it's very vague, you would assume that it's just a normal pulley problem because there's no other way to do use a pulley because it inverts the direction of the strings. So let's say M2 is the heavier one over here. Well, M2 is the heavier one, but let's just say um, well, I like putting it inside, makes it easier. So we have those forces, and then we have those forces. Actually, I think. Oh, it doesn't actually mention the surface it's on. Hmm. Hmm. Oh, I think I know what. I think what this question is asking for really is it's an it's a rooftop one. These are the worst. All right. So M2 is heavier, so it's gonna go fall down. All right. So you have FT. There we go. So you have F2, and you have FG. FG. Oh, sorry. AMB. There we go. So MA, yeah. And then you have FTA, FTB. Alright. So you have all that. Now we just need to find the acceleration of the system and the tension of the rope. Alright. So let's just set up some equations. So what is the direction of motion of the system? Well, it's going downwards, right? Because the heavier item is on the right side, therefore it must be falling down. So we can know the positive now. For A, we have F net. We have FTA positive because it's going on the direction, minus FGA, FGA. And then we can just simplify this, MA, FTA minus MAG. There you go. So it's quite simple. And now for B, in this case, it's gravity being the positive, so FGB minus FTB. Now we simplify all this to MBA equals MBG minus FTB. Alright, and now remember what we did before, the system equation, so A plus B, preferably capitals. So this is the one we care now, because this has the system acceleration. So M equals MA plus B. So this is the acceleration we want. We want that. So we just combine the things. Remember, the tensions cancel out in here. So we have the gravitational force of mass B minus the gravitational force of mass A. And yeah, there you go. Now, there's one more thing we should do in here, is simplify the masses. So we could do MA plus MB into A equals MB minus MA times G. There you go. Perfect. And then we divide this to find the acceleration. MB minus M times G divided by the mass plus B. And there you go. And now that we have the actual equation, we just have to start plugging in. So mass of B was 5 minus 3 times 9.8 divided by 5 plus 3. So therefore the acceleration will be around 5 minus 3 times 9.8 divided by 8. Oops. 5 minus 3. Oops. 5 minus 3 times 9.8 divided by 8. It would be around 2.45 meters per second square. There you go. So that's the acceleration of the whole system. Alright. So that's for part A, or for the actual acceleration. And now we need to find the tension. Alright. So tension. Which tension though? Well, the tensions are equal, so it doesn't matter. Oh yeah, you're right. So we can just grab any equation we have. So out of these equations right here, any of them have the tension, so we could use any of those. In this case, we're just going to be using the MA one, because that one already has the tension force is positive, so we only have to switch the gravitational force. So we'll use this equation and just rearrange it. So FTA equals A minus MAG. And guess what? Now we have the acceleration of the system. So that means we know what the acceleration is. So we know that FTA will equal to the mass of it was 3 times 2.45 minus 3 times 9.8. So tension force will be equal to around times 5 times 3. So you'll have 7.35 minus 29.4. Okay. That's not possible. Why are they... Oh, I made a mistake. Why are they subtracting? Oopsies. Yeah, as you can see, silly mistakes. So 2.45 times 3, we have 7.35 plus 9.8 times 3, 29.4. So the tension force will be equal to around 36.75 newtons. So that's the tension force right there. How much time are we on? 30 minutes. Okay, I think we can do maybe 2 more problems. One. Let's just do. Let's just do. Let's just do one with table friction, and that should be good enough. Because the only type of problems you're gonna deal with really is either on the rooftop or like on a cliff type table thing, and then you'll either have friction or no friction. So I don't want to waste your time, and so I think it is a waste of time going over a problem twice with friction, without friction, because all it changes is friction, you know. So let's just say a 4 kilogram object is on a frictionless table. Okay, and it's connected by string to a 2.8 kilogram object. Alright, and actually this one would be hanging. That would be hanging off the table. So the question here is, find the acceleration of the system. And guess what? What are you going to find here? You guessed it, the tension in the string. Alright, so first, what do we know? Well, we need to draw a diagram out. We have a, we can call this object A, and then this one is 4 kilograms, connected by a string to an hanging object. We can call this mass B, and this one is called, I actually forgot, 2 kilograms. There you go. Now, if you would have to do this with only variables, you would either have to call them A or B, or if you really wanted to, you do half of A equals B. That's for you tryhards out there. But yeah, that will actually come in handy quite in the future. Doesn't matter. So let's just do the forces here. Boom, 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 boom. And now we have friction on this table. So, and then we have FG, and then FGA, then we have FF, and then we have FTA, FTB, and then we have FGB. Alright, so those are all the forces right there. So very similar to what we already did before. Let's just isolate each one and find the net equations for all of them. So, um, actually, wait. In this case, hmm, no, sorry, never mind. Well, I'm just trying to find the direction of positivity. Hmm. Well, clearly it would still be down there, but would it fall? I don't know. Mm, 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 mm. Hmm. I don't know. I'm gonna say yeah. Because it wants to fall down naturally, so in its natural state, it would have to do that. So for F net A, we would have the FTA minus the friction force. Okay. And then we could just simplify this. A plus FTA minus mu Fm. And then simplify again, sadly. FTA minus mu. Oh, in a it's on a table with friction. I'm so used to writing frictionless. Mu equals what's a common number, like 0.110. I think that's pretty realistic. Yeah. So mu Fn ma, because Fn equals to the gravity here. So here you go. Now we just state B. In this case, Fn FGB minus FTB, simplify MPA, MBG minus FTB. Alright, now we find system, A plus B, there we go, MA, M equals MA plus MB. So we have to cancel out. So we have MBG minus mu MAG. Then we divide this by MA plus MB to find acceleration. So acceleration would be equal to this. So now we just need to plug in, right? So we have, actually there's not gonna be enough space for that. MB, what the hell was MB? 2 kilograms. So we have 2 times 9.8 minus 0.10 times 4. Yes, it was 4. It was 9.8. And then we have all of this divided by 2 plus 4, which is 6. So the acceleration would be around I'm gonna guess, not a whole number, minus, so we have 9.8 times 2, which is 19.6, and then we have 0.1 times 4 times 9.8, which is 3.92 divided by 6, so 19.6, and 2 divided by 6. So the acceleration would be equal to around 2.61 meters per second squared. So yeah, and now we can just grab any equation for tension, since now we know the which one can we use. Actually, doesn't really matter which one we grab. I'll just grab the all positive. In some cases, you might have to do the other one really, because sometimes they don't give you the mu, and you're expected to like skip the step of finding mu. Because let's just say you're dealing with this type of problem and they don't give you mu, but you can still solve it without mu. Um, Obviously you can't because of variables, but they expect you to know how to solve these type of problems with avoiding certain obstacles, so you can overcome them. Because there's always a lot of options for everything. All right, so the tension force should be equal to around 4 times the new acceleration, 6.1 minus 0.1 times 2 times 9.8. So FTA should be equal to around 2.61 times 4, 1.44 minus 0.1 times 2 times 9.8, 1.96. So FTA should be around 1.44 minus that, or 8 newtons. So it should be around 8.48 newtons for the tension force. Remember the FTB and the other one are equal. Um, shoot, I made a mistake again. I forgot, they're supposed to be adding. Gosh, I always make that mistake. 10 before plus 1.96. Should be around 12.4 newtons actually. There you go. Should be around there. Because, yeah. And you have well, the mu factor is you have mu. Yeah, should be fine. Yeah, 0.1. Yeah. Yep, so that's it. That's all the practice problems really. Yeah, remember just set of equations that you have to be doing that along physics anyways. So just get used to it. So let's go over it really, and let's just review. So what are the key concepts? Well, a pulley involves two or more objects that are connected by string or a rope. The tension in the string and the acceleration of the object are linked, and they are connected together. These pulleys are considered massless, and they are ideal because the tension is uniform. So some tips, obviously, use the free body diagrams for each object separately. You can do that within the diagram itself or somewhere else. Always assume the string is massless and it is inextensible. That does not mean stretchless. Ignore friction within the pulley, so that's internal friction, and only consider the following forces, which are tension, gravity, and the normal force, and then friction within surfaces. So same as normal force. So that's just an example of what it looks like right here, a common pulley problem. But another one is, this is a more detailed example right here. So this is how you would, so this is how you first of all draw the free body diagrams. This is how you draw the overall diagram. This is how you draw the statements because the tensions are equal. This is how you do the F nets for each object. And you get these from the free body diagrams you do here. Then you do the system, which combines both of these equations, so you add them together. And then you can find the acceleration or anything to do with the system right there. And then these are just practice problems, and these are another type of pulley thing. So these are connected to rooftop. And I think one more example of a pulley could be, if I remember correctly, I'm trying to remember, there's a tough problem on the AP exam with a pulley. It had to do with a tube like this, and then it was connected by a string. It was like this. So pulleys can get kind of weird, but yeah. Anyways, thank you for watching. Make sure to practice, and yeah, have a good day. Thank you.